Now we're going to talk about solubility equilibria. Now all ionic compounds dissolve in water to some degree. However, many compounds have such low solubility in water that we classify them as insoluble. We can apply the concepts of equilibrium to salts dissolving and use the equilibrium constant for the process to measure relative solubilities in water. Now let's talk about solubility product. The equilibrium constant for the dissociation of a solid salt into its aqueous ions is called the solubility product, Ksp. For example, the ionization or dissociation reaction for lead chloride is lead chloride as a solid breaks up in water to form lead ions in the aqueous phase and 2 chloride ions in the aqueous phase. Now its mass action expression is going to ignore the solid state of lead chloride. So the Ksp, the equilibrium constant, is equal to the concentration of lead ion times the concentration of chloride ion squared. So let's see if you can determine what the mass action equation for the dissociation of aluminum sulfide would be, A, B, C, or D. Well, if you chose B, you would be correct. It's going to be the concentration of aluminum ion squared times the concentration of sulfide ion cubed. When an ionic salt like sodium chloride is dissolved in water, the positive side of water molecules, the hydrogen side, is attracted to negative chloride ions of the salt crystal, and the negative side of water molecules is attracted to positive sodium ions. The salt begins to dissolve as ions are carried away to the aqueous phase. As long as some of the crystal remains, however, some dissolved ions may bump into it and deposit on the crystal surface. Eventually, a point is reached where the rate of ions leaving the crystal surface equals the rate at which they rejoin the crystal. A dynamic equilibrium is established, and the solution is said to be saturated. Remember that the solubility product is equal to the concentration of the ions that do dissolve at equilibrium to the power of their coefficient in the ionization expression. Therefore, the smaller the value of the solubility product, the less soluble a salt will be. Now, the molar solubility is the amount of solute that will dissolve in a given amount of solution at a particular temperature. The molar solubility is the number of moles of solute that will dissolve in a liter of solution. The molarity of the dissolved solute in a saturated solution. The gram solubility is usually expressed as grams of solute per 100 milliliters of solvent. Now let's calculate the molar solubility of lead chloride in pure water from its solubility product. The equilibrium expression is lead chloride in the solid phase, breaks up to form lead ions in the aqueous phase, and 2 chloride ions in the aqueous phase. So the mass action equation is the lead ion concentration times the chloride ion concentration squared equals the solubility product. Now we're going to let X equal the molar solubility of lead chloride. So X will be the amount of lead chloride that actually dissolves, and will form X molar of lead ions and 2X molar of chloride ions. So now we can fill in our ICE expression. For the initial concentrations, we have 0 for the lead concentration and 0 for the chloride ion concentration. And as the lead chloride dissolves and forms equilibrium, we form plus X molar of lead ion concentration and 2X molar of chloride ion concentration. This is because we're defining X as the amount of lead chloride that actually dissolves. So at equilibrium, we have X and 2X. Plugging X and 2X squared into our mass action expression, we get X times 2X squared equals 1.17 times 10 to the minus 5, the Ksp. And solve for X, it's 1.43 times 10 to the minus 2. Now let's turn the tables and see if we can determine the solubility product from molar solubility. If the molar solubility of lead bromide is 1.05 times 10 to the minus 2 molar, can you calculate what the solubility product would be for this compound? Turn your playback off, try it, and then come back and we'll discuss it. Alright, so here's our equilibrium expression. Lead bromide breaks up to form lead ions and 2 bromide ions. So we'll let X be the molarity of lead bromide that dissolves at equilibrium, forming X molar of lead ion and 2X molar of bromide ion. And we're given that X equals 1.05 times 10 to the minus 2. So our mass action expression is solubility product equals lead ion concentration times bromide ion concentration squared, and we plug in X for the lead ion and 2X squared for the bromide ion concentration. It's important to realize where this 2 comes from. It bothers a lot of students and causes a lot of headaches. It comes from the stoichiometry of lead bromide dissolving, because for every 1 mole of lead bromide that dissolves, we get 1 mole of lead ion and 2 moles of bromide ion. And therefore the stoichiometry is 1 to 2. Lead ion is X, bromide ion is 2X squared. So now we can calculate the solubility expression because we know that X is 1.05 times 10 to the minus 2. We plug that value into our expression here, and we get the solubility product of 4.63 times 10 to the minus 6. Okay, why don't you try this one? Turn your playback off, try the question, and come back, we'll discuss it. All right, we're supposed to find the molar solubility of magnesium phosphate given the solubility product value of 1.0 times 10 to the minus 25. So we write our equilibrium expression. Magnesium phosphate breaks up into 3 moles of magnesium ion and 2 moles of phosphate ion. Therefore, our stoichiometry, where we let X be the molarity of magnesium phosphate at equilibrium, the magnesium ion concentration will be 3 times that, or 3X, and the phosphate ion concentration will be double that, or 2X. Now we can plug these values into the mass action expression, which is the concentration of magnesium ion cubed times the concentration of phosphate ion squared equals KSP, or 1.0 times 10 to the minus 25. So we plug 3X in for the magnesium ion and cube it, 2X for the phosphate ion concentration and square it, solve for X, we get 3.92 times 10 to the minus 6. Now let's talk about KSP, solubility product, and relative solubility. Molar solubility is related to solubility product, but you cannot always compare solubilities of compounds by comparing their KSP values. In order to compare KSP values, the compounds must have the same dissociation stoichiometry. So to illustrate this, which salt, AB or CD2, has the higher molar solubility when they both have the same solubility product, 1 times 10 to the minus 9. So for AB, the amount of AB that dissolves at equilibrium we call X, and therefore A plus will be X and B minus will be X, or X squared equals 1 times 10 to the minus 9, or X equals 3 times 10 to the minus 5. Now let's look at CD2. CD2 we call the molar solubility X, and that breaks up into X of CD2 plus and 2X of D minus, and therefore plugging these values into our mass action expression we get X times 2X squared equals 1 times 10 to the minus 9. Solving for X we get 6 times 10 to the minus 4. So the molar solubility of CD2 is in fact greater than the molar solubility of AB. Now let's look at the effect of a common ion on solubility. Addition of a soluble salt that contains one of the ions of the insoluble salt decreases the solubility of the insoluble salt. Consider adding sodium chloride to the solubility equilibrium of solid lead chloride. So here's our equilibrium, lead chloride breaking up into lead ion and chloride ion. Imagine adding some sodium chloride to this mixture. Chloride is the common ion, common to sodium chloride and common to lead chloride. But what effect is the added chloride going to have on the equilibrium? Well, if you imagine that at equilibrium, the mass action equation, lead ion times chloride ion squared, will equal the solubility product. But when we add the sodium chloride, suddenly our concentration of chloride shoots up, and the Q value for that mass action equation is now greater than the solubility product. It's no longer at equilibrium. So what has to happen? The equilibrium has to shift to the left to use up chloride ion and lead ion in such a way that the ion product, lead ion times chloride ion squared, the Q value comes down to equal the solubility product. And then it stops shifting and equilibrium is restored. So for the solubility of lead chloride, if we add sodium chloride, the solubility of the lead chloride is going to decrease.
When a slightly soluble solid such as silver iodide is placed in water, an equilibrium is established between the ions in the solid and in solution. In this view, the water molecules that solvate the ions are not shown to simplify the illustration. The solubility equilibrium is expressed by the solubility product. The silver and iodide ions are of equal concentration in the solution. When sodium iodide, a soluble salt, is added, the concentration of iodide ion is greatly increased. This means that the product of the silver and iodide concentrations exceeds the solubility product constant. Because the product of the ion concentrations exceeds Ksp, additional solid silver iodide forms until the product of the iodide and silver ion concentrations again equals Ksp. At equilibrium, when the product of the silver and iodide concentrations equals Ksp, the silver ion concentration is much smaller than the iodide concentration. The addition of sodium iodide, which greatly enlarges the concentration of one of the ions in the solubility equilibrium, has reduced the solubility of silver iodide. This reduction in solubility is an example of the common ion effect.
Now let's calculate the molar solubility of calcium fluoride in 0.1 molar calcium nitrate at 25 degrees C. The solubility product for calcium fluoride is 1.46 times 10 to the minus 10. So first, we write the dissociation reaction and the Ksp expression for calcium fluoride dissociating into calcium ion and fluoride ion. Now here's the thing, if we let X be the molar solubility of the calcium fluoride, in other words, the amount of calcium fluoride that actually dissociates, it will form X moles per liter of calcium ion, but 2X moles per liter of fluoride ion. That's because the fluoride is coming from the calcium fluoride. So it's a 1 to 2 molar stoichiometry, and you have double the amount of fluoride as you do calcium ion. But there's a wrinkle in this problem, because initially you've got a common ion, the calcium nitrate, and the calcium from that is the common ion, and its molarity is 0.1 moles per liter. Initially you don't have any fluoride. The fluoride that forms comes from the dissociation of calcium fluoride. So the change is X and 2X, and then at equilibrium we've got 0.1 plus X, which is just about going to be equal to 0.1 moles per liter of the calcium ion. That's because X is a very small number. How do we know that? Because Ksp is a very small number. And when Ksp is a very small number, the molar solubility of calcium fluoride will also be a very small number. And X, a very small number compared to 0.1, so that 0.1 plus X is just about equal to 0.1. Meanwhile, we still have 2X of the fluoride, again, double because the fluoride is coming from the calcium fluoride and it's a 1 to 2 molar stoichiometry. of calcium fluoride to fluoride ion. So we can write the solubility product expression out and plug in for calcium ion 0.1 moles per liter and for the fluoride ion 2x squared. And we solve for x, which is going to be 1.91 times 10 to the minus 5. So here's a problem for you to try. At what concentration of lead ion will lead chloride begin to precipitate in a 0.3 molar solution of sodium chloride? The KSP for lead chloride is 1.17 times 10 to the minus 5. Turn your playback off, try it, and then come back, we'll discuss it. Well, here's our setup. The solubility product is equal to 1.17 times 10 to the minus 5, and that equals the concentration of lead ion times the concentration of chloride ion squared. That's your basic mass action equation. We plug in 0.3 for the chloride ion, we solve for lead ion, and we get a lead ion concentration of 1.3 times 10 to the minus 4. So now I can hear some of you screaming, "Why don't you double the chloride ion?" And the answer to that is because almost all of the chloride ion is coming from 0.3 molar sodium chloride, which breaks up in a 1-to-1 ratio to form 0.3 molar of chloride ion, not double. And yes, we could put 0.3 plus 2x, where 2x represents the amount of chloride coming off the lead chloride, but it's negligible compared to the 0.3 from the sodium chloride. And therefore, we just simply ignore it and plug in straight away the chloride ion from sodium chloride. That's why we don't double the chloride ion. Now let's look at the effect of pH on solubility. For insoluble ionic hydroxides and for insoluble ionic compounds that contain the anions of weak acids, like carbonate or fluoride, the lower the pH, the greater the solubility of these compounds. And the higher the pH, the less the solubility. That's because pH is associated with the concentration of hydroxide. Higher the pH is the increased availability of the hydroxide ion, and the lower the pH is the less the availability of the hydroxide ion. So if you think about this equilibrium of this solid hydroxide dissolving to form the metal cation and the hydroxide ion, think of it in terms of Lavoisier's principle. If we add acid to this system, if we lower the pH by increasing the hydronium ion concentration, the hydronium ion is going to react with hydroxide, forming water. So in effect, you're taking the availability of hydroxide ion away from the system, and the system responds by dissolving more, and the solubility increases. The same is true with an anion of a weak acid, like barium carbonate, which dissolves to form barium ion and carbonate ion. But carbonate ion reacts with hydronium ion to form bicarbonate and water. Bicarbonate also reacts with hydronium ion to form carbon dioxide and water. So you lessen the availability of carbonate ion, the system responds by shifting to the right to the more soluble barium ion aqueous and carbonate ion aqueous. So how will decreasing the pH or increasing the concentration of hydronium ion affect the solubility of these four compounds? Turn your playback off, think about it, choose your answers, and then come back and we'll discuss it. Okay, so we're decreasing the pH, we're increasing the concentration of hydronium ion. With calcium fluoride, fluoride is the anion of a weak acid, hydrogen fluoride. If we make more hydronium ion available, it will react with fluoride, taking it away from its availability to the calcium ion and increasing the solubility of calcium fluoride. Same thing with iron hydroxide, where the increased hydronium ion reacts with hydroxide, driving the equilibrium to the right to the increased solubility of iron hydroxide. Same thing with zinc sulfide. Decreasing the pH increases the hydronium ion concentration. It reacts with sulfide to form the weak acid hydrogen sulfide and therefore increases the solubility of zinc sulfide. However, the silver bromide is a different story because the bromide ion is the salt of a strong acid, hydrogen bromide, and therefore the solubility of silver bromide will be independent of pH and independent of the concentration of hydronium ion.